That's the video, but we don't need that. And then I'm gonna go to share screen. Share the screen. Okay, let's see if I can do that. Oh. All right, so I'm gonna go briefly over the handout I gave in class. Let me just check with Amanda. Amanda, can you see the page? It's kind of a bad. In fact, let me check if you're hearing me. Do I have microphones? Stop sharing. Can you guys hear me? Can you guys hear me? I think you can, but I just want to make sure. Hear me. Can you? I'm assuming you're hearing me. Yes, okay, good. All right, let me share screen, this one, share screen. What I would like you to do is to get the handout I gave in class. It's not, I don't have an electronic version of it, so I'm just using, I had to scan, and then the scan is not as good as the copy I had. So the first situation is you have a block of a max M, and it said there is friction, but there is no motion. So if there is no motion, this is still, so it's not moving. And if that is true, if you want to build a free body diagram, because it has mass, it has weight, because it's standing on a table, it has the reaction of table to the block. That's the normal force. Some of you has the microphone on. Yeah, yeah. There you go. And you have a pulling force F. But if there is no motion, the net of all forces must be zero, because acceleration is zero. Which means you gotta have some reactive force, and that is what type of friction is the static friction that is matching out this force. That's why I sketched the vector with about the same size. So that's the number one. Any question? Number two, you have a slide. There is friction moving down the incline, constant velocity, the same situation. Net force must be equal zero. So what are the forces on this person? The weight, normal force, and you set up your y, x-axis, and I like to indicate positive direction along the the direction of the motion itself. So gravity, normal force, and it is said there is friction. So if there is friction, you have some resistance to the motion that's called friction. Because there is motion, it must be kinetic. And because it's kinetic, it has an expression for it. Coefficient of kinetic friction times the normal force. In the previous problem, the static friction doesn't have an expression for it, unless you are talking about the maximum possible static friction you can get. So static friction can be zero or can go all the way to a maximum value, which is equal to a coefficient times the normal force. But it's not necessarily this. So then you have a normal force, you have gravity, and you have friction. And then if it moves with constant velocity, it means the projection of gravity force along the direction of motion, which is, if the slope is given, it means that mg sine of this angle theta, which is the projection along the x-axis, must match out the static friction. So mg sine theta positive, because I'm setting the downward direction as being positive, minus your kinetic friction must be equal 0. So kinetic friction must have a magnitude that is equal to mg sine theta. Okay?
I have a question.
Yes.
So that means there's no motion in that one, but if there's motion, it's going to be
the first one has no motion. It is said there is no motion. The
Okay.
second one has motion. Is a friction moving down the incline, so there is motion.
Okay, but there's no acceleration.
Friction moving down the incline and a constant velocity. If the velocity is constant, therefore your acceleration must be 0.
Okay, but let's just say if there's an acceleration in there, it will be mg sine of theta minus friction, kinetic friction will equal to ma instead.
If there is acceleration, that would be some acceleration, yes. Yes.
Okay, got it.
And then your velocity wouldn't be constant. So, but in this situation, it is equal to 0.
All right, got it.
Okay. Okay, I think I have to go down. I have to stop sharing and go back to my paper. Go down. 2 more examples. Go back here. Share screen. One. Okay. So the next situation is you have a pulling rope. Okay, so you have the same situation as before, except you have a pulling rope, friction, and moving down the incline at constant velocity. So imagine somebody is going down the slope attached to a rope and moves down with constant velocity. So the key here is velocity is constant. It means the acceleration along that direction is 0, which means the sum of forces along that direction must be equal 0, because there is no acceleration. So when you do your free body diagram, in this case, you go back to what we did before. You have your weight, normal force. Now there is a rope that is giving some tension to that person. The person moves down with a constant velocity. So it means there is a friction which is kinetic against the direction of motion, okay? Which means the projection of gravity along the direction of motion, which is this. Oh, my vectors are not of good size, but your mg sine theta, must match out the sum of tension and kinetic friction. In other words, the sum of forces in the x direction, because must be equal 0, because the velocity is constant, is such that mg sine theta minus the tension of the rope minus kinetic friction that goes against the direction of motion must be equal 0. So that's what we got in x. And what we got in y direction is that your normal force is equal to mg cosine of that angle theta. Is that good?
Yes, it is.
What?
I got it.
Okay, very good. Okay, the next one, I'm not gonna do it. We did in class 2 times. Is that okay?
Yeah, I remember that one.
Okay. Amanda, is that okay? Are you good?
Yes.
Okay. All right, let me just get out of here. So the next problem is kind of the same idea. So you have a dude. Wait a second. You have somebody that is, there is a pulling rope and there is friction, but that person is being lifted. So it's going, the direction of motion is up and the velocity is constant. So if the velocity is constant, therefore acceleration is 0. That's the mantra. And then you go down to write down your forces. You have your gravity force, you have your normal force. Now, because the motion is upward, up the incline, therefore your kinetic friction is opposing the direction of motion, and your tension is still pulling up. So the direction of your tension force doesn't change. When you do your free body diagram, you can now set the direction of motion, your x direction, upward. As I mentioned to you, I like to call my positive direction the one that matches the direction of motion. Therefore, T has a positive sign, kinetic friction has a negative sign, as well as, look at this, the weight projected along x. So your mg sine theta also goes the other way. And this must be equal 0. So it is very common, students, when they project the gravity along x, to give a positive sign right here. It's not. So when you project, you have to take the tip or the head of your vector and draw a perpendicular to the x-axis. You have to make a 9 degrees angle, so you cannot possibly go upward on that, okay? And as you can see, the direction of your projection is downward. Question on that one? Is that okay?
I have a question?
Yes, Amanda, go.
Okay. In the other problems, I understand, but in this one, why is it sine?
Why is it what?
Why are we using sine for tension minus friction, kinetic friction minus mv sine?
Sine theta? Yes. Let me erase all of this. Just a second. Just one moment. Hey, babe, just a second. Just a second. Wait a second. Wait a second. Wait a second. Hi. So what happened with you? Yeah. Sorry about that. My daughter, she's having some problems with her eyes. Okay, so are you guys there? Oh, Amanda. Amanda had a question. Okay, so look at this. I'm putting in. Oops, that's the wrong one. Sorry. Annotate. Let's see if I can do it now. Why can't I go back to my pencil?
Try clicking the arrow key again, and then on your left.
Arrow key, I did. Mouse. And then I go to annotate. And then I should have a pencil, but it goes back to this crazy thing. Let me see if I can take this out. Mouse. I don't want this. I don't want eraser. Mouse. Annotate. Okay, let me stop sharing. And start sharing. No, wait a second. Why is this happening? Redo, clear all drawing. Annotate. Oh God. Don't save it. Just a second. Back to the meeting. Stop share. Okay. Now share the screen. Where's my text? No, that's not what I want. go to Toolbar. No, I have to go to my email. It's right here. View, rotate view, view, rotate view, clockwise, view, clockwise. And then we go down. That's the last one. Go to the meeting, back to the meeting, and share the screen. Annotate. Okay. So so you have an incline that has an angle, right? Oops, that has an angle, theta. Have a box in there. In fact, let me now the forces are gravity, and gravity is mg, and you do have a normal force that goes perpendicular to this incline. Is that correct? So far, so good. So I'm stopping on these two forces here, right? And then what you want to do is to find out where the weight is going to be along x and y. So this is your y, this is your x. Is that okay so far?
Yes.
Okay. Now look at this. This angle is theta, right? This angle here is 90 degrees. Why is that? Because this is the base of your incline, is horizontal, and the weight goes normal to the horizontal. It goes vertical. And a vertical makes a 90 degrees with the horizontal. So if this angle is theta, and if this is 90 degrees, therefore this angle up here is what? 90 minus theta. So think about theta 30 degrees. If theta is 30 degrees, this angle up here is 60 degrees. 90 minus 30. Is that okay?
Yes.
Okay. Now, at the same time, your normal force as well as your y-axis, they both make an angle of 90 degrees with x-axis. So if this angle is 90 degrees and this angle is 90 minus theta, therefore this angle here must be theta. Okay? So the point is, you want to project gravity. Let me change color. You want to project the gravity in your x-axis, and you want to project gravity in your y-axis.
Oh, okay.
Now you go to your SOHCAHTOA. So cosine of theta, see theta right here? Cosine of theta. So if you think about SOHCAHTOA, so cosine is the adjacent over hypotenuse. So cosine of theta is the adjacent, which is this thing over here. Right? Let's call this Amanda. Cosine theta is Amanda divided by hypotenuse, and your hypotenuse is mg. All right? So Amanda is mg cosine theta. So this over here is mg cosine theta. Now, sine. Sine of this angle theta, sine of theta, is equal the opposite side, this one, and let's call 3.
Oh, I think I got a leap right now. I have class.
All right.
Thank you.
So sine theta is 3 divided by mg. So t is 3 is mg sine theta. So t appears up here. It's the same side. So this is mg sine theta.
Okay.
So mg sine theta is going to be in x as long as this is theta. And
Okay.
mg cosine theta is going to be in y as long as this is theta. Is that okay?
Yes,
Okay.
makes perfect sense.
Okay. Now let's go to, I'm going to stop sharing. Let's move the page forward. I think I have to go to my email. Where's the other page? Oh, there you go. And that's it. Go back to here. Share screen. There. Okay. So let's write down free body diagram on this hanging mass. Hanging mass. What are the forces on it? Weight,
Yeah.
Fg, which is mg. And then you have a tension T2, like that. And you have a tension T1 up here. So look at the direction of those vectors. So gravity down, T2 somewhat upward, T1 somewhat upward. Now you have to remember your geometry. So what I'm doing is getting my x-axis like that. Oops, what did I do? What did I do? Go to the mouse, notate. And this is my and this is my y-axis. Okay. Now this angle between T2 and x-axis is giving 40 degrees. Okay. So it's not moving. So the block is stationary. So sum of all forces in x must be equal to 0. Since it doesn't move in y either, sum of all forces in y must be equal to 0. So that is funny. That is an impossible situation. So what are the forces in x? T2 cosine of 40 minus, there is no other force in x. So this is equal to 0. If this is true, it means that T2 is equal to 0 Newton. T2 does not exist. It's a string that has no force on it. Does that make sense?
Yeah, so it's just going to be the tension in y.
There will only be tension in y, correct. So when you do your sum of forces in y, T2 plus T1 plus T2 sine of 40 minus the downward gravity is equal to 0. But T2 is 0. So T1 is equal mg. Okay?
Okay.
Now, for the other, it's a little bit different now. Now you write the forces in here. mg. I can't even read in my handout. T2, I think. I think this is T1.
And 40 degrees.
And I have an angle of 40 degrees here, right?
Yes.
40 degrees there.
It's showing T2 has 60 degrees.
And T2 has 60 degrees. I can't even see in there. So 60 degrees in here. Let me, I'm afraid of erase and then clear all drawing. Okay, let me see, go to annotate again. Oh, cool. So let me do that again. So I have mg. You said 60 degrees here, right?
Yes.
60 degrees. This is T2. This is T1. And I think you said 40 degrees in there. Does not move. Sum of forces in x equals 0. Sum of forces in y equals 0. What do we got in x? Here's my x-axis. That's my y-axis. Positive, positive. In the positive x direction, T2. Now, the adjacent. I'm bringing T2 to the adjacent part of this angle, 60. Oh, Lord, I hate that. Oh, see, I bring my... Oh, God, why am I doing this? Why is this happening? Okay, oh, Lord. Oh, jeez. I have to improve my technology. Why I keep doing this? Wait a second. Oh, God, you got to be kidding. 3, what should I do? Oh, okay, it's gone. Eraser. Gone. Mouse. Go to annotate. Mouse. Annotate. Annotate. So T2 cosine of 60 positive minus T1. Now look at this. T1 projected in x, which is this vector over here. It is. What should you write?
Sine?
Sine. Very good. Sine of what?
40?
40. Good for you. So T2 cosine of 60 minus T1 sine of 40. That's it, right? mg is 0. The projection in there. That's what you got. And then you have some way to relate T2 and T1. Okay. And now the other one is when you project it in y. So T2 sine of 60. Now I'm projecting y plus T1 cosine of 40 is equal mg. So I could now replace T2 in this equation. T2 is T1 sine of 40 divided by cosine of 60. And that's what I will do. So T1 sine of 40 divided by cosine of 60 times sine of 60 plus T1 cosine of 40 is equal whatever mass that is. What is the mass? Is 40?
10.
10?
Yes.
10 times G, 9.8. And then we can find T1. T1 is equal, I'm not gonna do all the calculation. I don't have a calculator here.
Okay.
And that's not the point, but you guys could do it later. It's gonna be that divided by sine of 40 over cosine of 60 times sine of 60 plus cosine of 40. And then once you find T1, you plug it in here to find your T2. Okay.
Okay.
Let me clear this. And now we have a different situation is the mass, and you have 3 chords. So I'm gonna do the same thing, put T, I don't know, this looks like T3, and this looks like T2, and we have T1 right here, and there is an mg going down, and the mass is 50 kilograms. So the weight is 50 times 9.8. That is the weight.
Mm-hmm.
So same mantra, sum of forces in x equals 0. There is no motion. That goes, this angle here is 20, right?
Yes.
So in x, T3 cosine of 60 minus T2 will project in the opposite direction. So I'm calling this my x-axis is positive. I'm calling upward direction my y positive. So T3 cosine of 60 minus T2, as you said before, sine of 20. And minus T1. T1 is totally in x. This is equal 0. Now, I don't want you guys to go too complex here, right? You don't need, you're not gonna ever see this in an exam of 1 hour and 15 minutes. So I will outline only the equations. So don't get too crazy about it. So sum of forces in x is this. Sum of forces in y is equal 0, 2. So what do we get in y? T1 projected in y is 0. This T1 does not have a projection in y, but I do have a T2 cosine of 20 plus T3 cosine of, T3 sine of 60 minus 50 times 9.8 is equal 0. So those are the free body diagram in this case. But don't worry about solving. I just wanted you to outline the free body diagram. Solution is complicated, and even in this case, you can't solve because there are only 2 equations and 3 unknowns. Okay? I think the point is, okay, what are the forces in there? All right? Mm-hmm. Okay, 3?
He's gone.
Oh, he's gone? Oh, I can see it. All right. Now, the next one is a free body diagram for each mass. So we have 3 masses, and they are connected, like a tutu train. 1, 2, 3, Let's call this M1. That's the pulling locomotive. M2, M3. If there is friction, so you start with M3. If there is friction, rolling friction, you have your weight, M3G. G is 9.8. We have a normal force on it, and friction, which is kinetic, effective rolling friction, and you have a tension cord that pulls the train forward. Now, if you go to the mass M2, there is the weight, M2 times 9.8, normal force. The reaction of that T3 has the same magnitude but opposite direction. There is also a rolling friction, and there is a tension T2 over there. And if you go to the mass M1, you've got a weight, which is M1G, a normal force. There is a thrust. I mean, the locomotive has power, right? So it's a force that the locomotive itself is responsible for. And T3, and well, I'm calling this T2, I'm sorry, T2, and there is some rolling friction of this locomotive there. Okay, so 1, 2, 3, 4, 5. Good enough?
Yes.
Let me erase all of that. And I don't want to get back. I have to do something else. I have to leave it. So I'm completing the last two ones. So we have a car pulling. You have a car that pulls something like this. So a car that pulls a trailer. So on the car, you have the forward pull that is provided by the engine, or thrust, if you will. You do have some friction, rolling friction in the tires. You do have your gravity force, weight, and you do have your normal force. But this is connected to a trailer, so you have a tension force that way. Now, the magnitude of this tension force is the one responsible for pulling the trailer forward, but with the opposite direction. As you can see, you do have your rolling friction, you do have your weight, mass of trailer times 9.8, and you do have your normal force. Now, Amanda, don't you see this is all kind of a mechanical?
Yes.
Yeah. I mean, after you get the hang of it, it just go forward. Okay.
It's very helpful.
Okay. So the last one that I would do is the two mass. It's called Atwood machine.
Mm-hmm.
So you have two masses here. If this pulley has no weight, then it is true the tension in these cords are the same. But later on, we are going to learn situations in which the pulley has mass, and then this is not going to be true. But right now, this is the case, ME1, ME2. So if you look at ME2 mass, you have the weight of it, and you have a tension. And if you look at ME1 in the other side, have the weight, and the tension is the same. I don't know. Oh, it's moving down. It means ME2 must be bigger than ME1. That's all. If you look at the pulley itself, pulley has an upward holding tension and a T and a T down there. So this T is equal to T, basically, since the pulley is not moving and has no mass, okay? All right?
Okay.
Okay, all right.
Thank you.
All right, have a nice one.
You too. Bye.
Bye.